This is welcome to the second session out of, I think, something like 18 on reinforcement learning here. First up, we have Maria Di Lacapoulou, who's going to talk from Stanford and going to talk about coordinated exploration in concurrent reinforcement learning.
Thank you. Hello, I'm excited to be here. My name is Maria Di Lacapoulou. I'm a PhD student at Stanford, and this is joint work with Professor Ben Van Rooij. Today, I will talk to you about a new concept and algorithm in concurrent reinforcement learning, and we will see how this new concept can be used to enable rapid learning of effective policies when we have multiple agents learning to operate in parallel in a common environment. For instance, imagine a farm of robots learning how to carry out a task, collaborating and sharing data with one another in real time. A large number of robots can gather and share a much larger amount of data in the same amount of time. There are benefits to scale, but these benefits are most dramatic when the robots coordinate the way they explore their environment. So say that the task is to learn how to swing up, balance upright, and center a pole that is attached to the cart. The cart moves on a rail between two bouncing walls, and the pole starts by hanging downwards. The robot can tap the cart left or right, or do nothing, and tapping incurs a tiny cost. The reward structure is very sparse. Only when the pole is steady, balanced upright, and the cart is centered between the two walls, only then the robot observes a reward. Otherwise, there is no reward. This is a hard problem calling for deep exploration, and a single agent, depending on its exploration strategy, will need from many hours to an exponential amount of time to learn the task. Now imagine that instead of a single agent, we have a bunch of agents collaborating to solve the problem. Each agent has its own car pole and controls it independently from all other agents. the agents interact with their card pools in parallel, and they share data with one another in real time. Therefore, each agent has access to the observations of all other agents before making any new decision. Here is how the behavior of epsilon-greedy agents looks like. As we see, there is not much progress, and even with a large number of agents gathering large amounts of data in parallel, an exponential amount of time will be needed to learn this task. And changing the value of epsilon for the epsilon-greedy agents is not the thing that is going to solve the problem. Instead, deep exploration and coordination among the data gathering among the agents is the key to effective team performance. Now, we are looking at an algorithm that does achieve the deep and coordinated exploration. Exploratory actions play an important role, and structured diversity of the experience may greatly accelerate learning. With coordinated exploration, as we increase the number of agents, we can learn complex tasks very quickly. In our example, the task can be mastered in a matter of seconds. So this was seed sampling, the algorithm I will present you today. But first, let's define our concurrent reinforcement learning setting concretely. We have K agents learning to operate in parallel in a common environment, in different instances of that same environment. The environment is modeled as an MDP. The agents interact in parallel, synchronously or asynchronously with the different instances of the environment, and they can interact over a large or even infinite horizon. The agent starts with common priors over the unknown transition and reward dynamics of the Markov decision process. There is perfect information sharing among the agents, and in real time, the common posteriors are updated. The goal of the agents is to maximize the reward accumulated by the group. Silver et al. Introduced concurrent reinforcement learning in a web service application where a customer was served by an agent and the customer interactions were in parallel and asynchronously. Since then, some UCB-based algorithms have been proposed for concurrent reinforcement learning, but as we will see, UCB approaches are not suitable for this setting, and sometimes they do very bad. In robotics, concurrent RL has been used as means to gather more data in the same amount of time. But considering its importance, the issue of coordinated exploration and concurrent reinforcement learning has received surprisingly little attention. Our work aims to structure and coordinate such exploration in a systematic and robust manner. We have identified 3 properties which are necessary for efficient coordinated exploration. First, real-time adaptivity to observations among agents. In the card pool example, each agent needs to adapt its policy with respect to the card pool it controls based on the observations made by all agents from their interactions with their card pools. Second property is commitment of each agent to carry out action sequences that span multiple time periods. Each agent in the card pool problem should commit to control its card pool in a certain way for a period of time long enough to yield a successful outcome or to contribute valuable information for the learning of the group. And third property is diversity across the learning opportunities pursued by different agents. The agents should diversify the way they control their card pools in order to contribute useful data to the group. And as we will see next, these properties are necessary for designing reliable reinforcement learning algorithms for the concurrent setting. But they are not satisfied by straightforward extensions of PSRL or UCRL, which are the effective exploration strategies in the single agent setting. The optimistic approach in concurrent RL is that in each time period throughout learning, the agents will construct the same confidence bounds because they have access to the same posterior. The problem with this approach is that it is deterministic, and as such, it doesn't diversify the exploratory efforts among agents. As a result, with concurrent UCRL, all agents will construct the same optimistic model of the environment, and from the same state, they are going to take the same action. To understand the importance of the diversity property, consider this toy example of parallel chains. The agents start from the source node, and each agent has to choose one chain and wishes to choose the chain that yields the maximum reward. Now, everything is known in this problem apart from the reward of the last edge of each chain. These rewards are independent and normally distributed with mean 0 and variance that increases as we move from the top chain to the bottom one. Now, concurrent UCRL is going to direct all agents initially to the bottom chain because it's the one that is most optimistic. As a result, concurrent UCRL agents do not divide and conquer when we have multiple facets of the environment to explore. On the other hand, naive extensions of single-agent PSRL do not work well either. One approach would be the concurrent PSRL, where each agent at the beginning of learning draws a model from the common posterior, and this model remains fixed throughout the course of learning and only updated at the end of learning based on all observations from all agents. But this approach doesn't adapt the learning of each agent to the vast amount of data gathered by his peers. Another extension of PSRL would be Thompson resampling, where in each time period, each agent resamples a new MDP from the common posterior in order to accumulate the information gathered so far. Now, this adapts to the latest information, but resampling a model independently in each time period from the common posterior may break the agent's commitment to action sequences that span multiple time periods. To understand the commitment of the importance of the commitment property, consider this example of the chain, where this chain has opposite rewards of large absolute value in the endpoint edges. Everything in this example is known apart from which endpoint edge has the positive reward and which endpoint edge has the negative reward. The agents will start from the middle of the chain, and in each time period, they are going to resample a new MDP from the common posterior. But with this independent sampling, the endpoint edge with the positive reward may change from one sample to the next. As a result, the Thompson resampling agents will dither left or right, incurring unnecessary costs from the negative middle edges, and most importantly, not making progress in the exploration of other endpoint edge. So we propose seed sampling, which is a novel extension of PSRL that does satisfy the commitment, adaptivity, and diversity properties. At the start of learning, each agent samples independently a random seed. This seed is unique for each agent and stays fixed throughout the course of learning. Now, this seed is mapped to an MDP through a deterministic function. And this deterministic function is common across agents and reflects the common posterior beliefs of the agents. Here is how the necessary properties of efficient exploration are satisfied. First, the deterministic function is updated in each time period to incorporate the data gathered by all agents in each time period. So the agents can react intelligently to new information as they come. Second, the seed that each agent draws in the beginning of learning independently ensures diverse exploration of the environment, even with a common posterior among agents. And third, the fixed seed throughout the course of learning for the same agent induces temporal correlations among the samples drawn by this agent, ensuring commitment. There are several seed sampling schemes one can come up with. And here we show three of them. So if we wanted to draw transition dynamics with a Dirichlet prior, each agent could use sequences of standard exponential seeds. Or if we wanted to draw reward dynamics from a Gaussian prior, each agent could use a standard Gaussian seed or do Kalman filtering using a seed, a sample from the prior, and noise samples combined. However, seed sampling transcends specific schemes, as the ones I show here, and offers a general mechanism in designing efficient coordination algorithms in the concurrent setting. To illustrate the behavior of the different approaches, we will now look at an animated demo. And as an environment in this demo, we are going to have a large maze, and somewhere in the maze there exists a big round of cheese. The round of cheese can be in any of these question mark locations with equal probability. Now we have a bunch of mice navigating the maze and trying to find the cheese. Each mouse has a map of the maze with the potential locations of the cheese, and it also has a walkie-talkie to communicate in real time with all other mice. When a mouse explores a question mark location, all other mice learn whether the cheese was there or not. So the shared posterior among the mice is a uniform distribution among the potential viable locations of the cheese that remain, that are unexplored. So Thompson resampling is going to change the target in every time period. Thompson resampling mice do not manage to do any progress because they change where they are going with an independent target in every time period. An improved version of Thompson resampling one can think of is don't sample in every time period, only sample when the common posterior is updated. So when a mouse goes to a question mark location, the common posterior of the mice is updated, and only then the mice draw a new target to pursue. But even that causes unnecessary dithering because the mice do not commit to explore a target all the way to the end. Instead, when new information comes in, they are going to resample where they are going. Eventually, they will get to the cheese, but this is going to cause unnecessary delays. Now, the concurrent UCRL mice are very optimistic. They say the cheese cannot be very far enough, so let's all pursue the target that is closest to our position. Each mouse wants to be optimistic, and they pursue the same target. They do not divide and conquer over this large maze, and again, this lack of diversity in the exploration is going to delay the discovery of the cheese. And finally, we have the seed sampling mice, which do divide and conquer, but they also commit to a target to pursue, and this is why they find the cheese very quickly. Now, in that problem, the seed of each mouse was a random permutation of the initial question mark locations. Each mouse had that list, and every time a mouse were exploring one of the locations, all the mice would cross off this location from their lists. Then the mice would go to the target that was at the top of their list and hadn't been crossed off. So in the parallel chains example we saw initially, we highlighted the importance of the diversity property. Seed sampling with the independent seeds and Thompson resampling with the independent MDPs do diversify, but concurrent UCRL does not. So on the left plot, we see the cumulative regret for a fixed number of agents. The regret is on the y-axis, and on the x-axis, we have this fixed number of agents ordered in increasing time that they left the source. We see that due to the wasteful allocation of the agents, the concurrent UCRL agents get to the point of zero regret only for the last few agents, unlike seed sampling. On the right, we see the average per agent regret as the number of agents thrown to the problem increases. Concurrent UCRL does not benefit much from increased resources, whereas seed sampling will. Now, with the bipolar chain, we demonstrated the importance of the commitment property. Concurrent UCRL, thanks to its deterministic nature, and seed sampling through the fixed seeds, are able to commit. However, Thompson resampling agents are going to dither. And on the left plot, we see how, for a fixed number of seeds, this dithering is detrimental in the cumulative regret performance. And on the right plot, we see that even increasing the number of agents thrown to the problem, it doesn't solve the issue that dithering causes, whereas concurrent UCRL and seed sampling here are going to decrease their mean per agent regret very fast. And finally, let's revisit the cartpole problem, which is a more complex problem and realistic in terms of reinforcement learning than the toy examples I showed you. We simplify the problem by making the rail infinite and by removing the walls, and hence the requirement that the cart is centered. We do that so that we make the problem of sufficiently small scale to be addressed by tabular methods. However, even in this simplified version of cartpole, deep exploration is necessary because the reward structure does remain sparse. So all the algorithms start with uninformative Dirichlet priors over the transition dynamics and uninformative standard Gaussian priors over the reward dynamics. And we compare seed sampling with the three other baselines we discussed. Now, we give each agent a cartpole to interact with for 20 seconds. And after the 20 seconds of learning, we evaluated what the different agents learned. We see that as we increase the number of agents, seed sampling is able to increase its evaluation reward very quickly and achieve high rewards over a very fast period of time, over like only 20 seconds of learning. On the other hand, the evaluation reward achieved by episodic PSRL that does not adapt, a concurrent UCRL that does not diversify, and Thompson resampling that does not commit are not able to increase the reward at all or increase it very slowly as the number of agents increases. To conclude, concurrent RL is poised to play an important role in a wide range of applications, ranging from web services, where a customer is served by an agent, to autonomous vehicles, where a vehicle is controlled by an agent. By satisfying the adaptivity, commitment, and diversity properties, seed sampling efficiently coordinates for the achievement of a common goal by multiple agents. And we envision that when multiple agents are available, seed sampling will enable the learning of complex goals very, very quickly. Thank you.
All right, well, we're having questions. Could the next speaker come up? Is there any questions? I should say, I had to use one of the two mics here, so the only mic that works is that one there, so if you can go to that one. There's no microphone in this one, just on that one.
Interesting work. Just to understand it correctly, let's say I have a K agent. Can we reduce the learning time from T to T by K?
So when we have, as we increase K over a large or even infinite horizon, then the mean regret per agent is expected to go to 0. That's a desirable effect. As we increase the number of agents, the regret that each agent experiences is going to 0.
OK, so you're quantifying the regret. But do you know how fast it goes to 0 with respect to T?
This is future work.
Thank you.
Thank you.
Take one more while the speaker's setting up. Yeah.
Hi. Can you explain mathematically how do you formalize commitment via seed sampling?
So with the commitment, we have a few properties. We can say that for when the procedure doesn't change much, so when we have no new information, then the model drawn by every agent will not change at all. Now, if we have some information, there is going to be some smoothness on the way the next model that integrates the new information is going to change.
Thank you.
All right, let's thank the speaker. Next up, we have Krzysztof Choromansky talking about structured evolution with compact architectures for scalable policy optimization.
It's a great pleasure to give this talk. Google Brain Robotics team in New York and Cambridge University. It's a joint work with Mark Rowland, Vikas Sindfani, Richard Turner, and Adrian Weller. So what is the goal of this talk? We want to present a novel way of learning optimal policies for reinforcement learning using evolution strategies. So the policy is encoded by the neural network. The input vector is the state vector. The output vector is a proposed action vector. And we think about it as a black box optimization problem, where the input parameters of the black box function, the input arguments, are the parameters of the neural network encoding the policy. And the output is the total reward obtained by an agent applying this particular policy in the given environment. If we think about it from the optimization point of view, I mean, we really want to maximize this function. The ancient way of doing this would be just sense the gradient using standard finite difference method. It's not very efficient because we need lots of perturbations to collect these outputs of the function, and this is a bottleneck of computations. What we come up here is a way of doing many perturbations at the same time, and in such a way that the direction describing perturbations are pairwise orthogonal. So this is what we call gradient sensing with randomly rotated basis. And it's somehow related to a paper that was introduced a couple of years ago when guys from OpenAI proposed to use Gaussian directions as perturbations to approximate the gradient. However, what we want to really focus on here is the orthogonality, because by assuming that the directions are pairwise orthogonal, we can actually reduce the variance of the estimator, of the gradient estimator, and that's the key point to get better quality sensing. So let's just note like one thing, like these Gaussian methods are related to something that we call the Gaussian smoothing of the black box function. So we do not really optimize the function itself, but a smoothed version of this function. And if we think about it this way, then the methods, like the Gaussian methods, both our methods and OpenIGM methods, is basically unbiased Monte Carlo estimation of the gradient of the Gaussian smoothing of the function. And on the top of that, we can use gradient-based methods to compute optimal policies. And this is the case because the gradient of the Gaussian smoothing is given by this expectation right here in the blue box. So we can come up with Monte Carlo estimators. Standard way of doing this, the bunch of unbiased Monte Carlo estimators with different control variant terms. What we propose is to instead use pairwise orthogonal directions instead of using Gaussian unstructured. And that reduces the variance of the estimator. It's not clear like what control variance terms like, would be optimal in this setting. However, the point is that like for all these unbiased estimators, we can use orthogonality trick, and it improves the quality. So one thing that I want to mention is the orthogonal trick is not valid like only here, like in the policy learning setting, but actually it was applied successfully in kernel approximation with random feature maps, GLT, recently even recurrent neural networks. So the theoretical result that we have, it's basically a motivation for like why it works is the result saying that the mean squared error of the gradient of the Gaussian smoothing using orthogonal directions is strictly smaller than the mean squared error of the gradient of the Gaussian smoothing, of the estimator of the Gaussian smoothing using standard unstructured directions. And we know exactly what this difference is. And of course, like the intuition is that better quality estimation should lead to better quality policy if we use some gradient-based method on the top of that. And now, the problem with Gaussian orthogonal stuff is that it's not very efficient if you want to sample orthogonal directions at every iteration just because you need to do Gram-Schmidt orthogonalization. And you don't want to do it like with policies of thousands of parameters. So is it the case that we have a system that produces more accurate estimator, but actually it's not very efficient? That might be the case, but fortunately there are two tricks that we can apply to make it work. And the first trick is to use approximation of Gaussian orthogonal matrices. One way of doing is take products of random Hadamard matrices. The orthogonality is embedded in the structure of the Hadamard matrix, and the randomness is given by random diagonal matrices with +1, -1 entries. And they work like reasonably well. Actually, they outperform Gaussian orthogonal matrices on a bunch of reinforcement learning tasks. But of course, you don't need to do any orthogonalization because it's embedded in the structure of the matrix. The problem with this approach, however, is that those matrices are defined the Kronecker-based Hadamard matrices are defined just for powers of 2, rows powers of 2. So now how we can get around this, and one option is to use what we call Kamas matrices. That stands for Katz random walk-based asymptotic random orthogonal matrices approximators, where basically the approximation of the Gaussian orthogonal matrix defining the directions of gradient sensing is given by the product of low-dimensional rotations, actually two-dimensional rotations, product of Gibbons matrices. The nice thing about it is that it's defined for any dimensionality. We don't need to add any zero padding stuff. It's just much simpler than the Hadamard mechanism. And the name of this actually mechanism is very close to my heart because this is a short version of my fiancé's name. So, and it's a much better version of the standard Hadamard approach. Now, the other trick that we can apply is to make the policy much more compact, using basically structured matrices, learned structured matrices to encode the neural network. What we did here in this paper, we used feed-forward neural networks to encode the policy with 3 toplets matrices, and that basically gives us the reduction of the number of parameters from quadratic to linear. So the number of perturbations that we need actually to make to accurately sense the gradient is actually much smaller. And those structured policies work very well in practice. They, in fact, outperform unstructured ones. So this is a bunch of experimental results, low-dimensional tasks when we compare OpenAI, orthogonal methods like with unstructured methods, and they consistently beat unstructured ones. And also the robotics tasks. So Adam optimizer with standard, gradient sensing, and then our gradient sensing with structured matrices for gradient sensing and for policy encoding. What we managed to do is compress the number of parameters of the policy, at the same time learn good quality policies. So all these videos that you see here, I basically learned with structured matrices and structured gradient sensing, and the parameter is the number of parameters of the policy that you need to learn these behaviors. So it's a much more compact version of what was done before. And at the very end, the learning curves that we get for a bunch of OpenIGM tasks, where we basically compared our approach with the standard one. So to sum it up, there are two main tricks. Structured gradient sensing to reduce the variance of the estimator of the gradient of the Gaussian smoothing, and structured policies to reduce the number of parameters and in this way, the number of perturbations that you need to do to sense the good quality approximation of the gradient. Thank you so much.
All right, while we're taking questions, let's have the next speaker come up. So I had a question. If, since large Gaussian matrices, if you normalize them, are approximately orthogonal anyway, can you give some notion about why this is so much better than a random Gaussian?
It's a very good question. Like, people ask me very often, like, if you take a Gaussian matrix which is not orthogonal, I mean, the product is, like, roughly speaking, 0, right? Like, why it makes sense to why it makes a difference. So the point is that you know, the reason is that when we actually apply these matrices, it's not just, we apply it like very often. So I think it's like this cumulative effect that like we need to, the fact that we have like orthogonality, it really makes a difference. The other like way of thinking about it, like for people like with quasi-Monte Carlo background is, those matrices lead to lower discrepancy of your estimators, and this lower discrepancy basically translates to lower variance. So even though it seems that at first glance that it shouldn't make a difference, it actually does. But the benefits depend on the application, and here is actually pretty huge. Thank you for the question.
All right, let's thank the speaker again. Next up, we have Yangxiang Gao, who's presenting Spotlight, which is the title of the paper, right? Not just, not that it's a spotlight, but Spotlight Optimizing Device Placement for Training Deep Neural Networks.
Hello, everyone. It's my great honor to be here to present our work, Spotlight Optimizing Device Placement for Training Deep Neural Networks. I'm Yuanxiang Gao, and this is a joint work with Li Chen, Baochun Li from University of Toronto. As we know, today's neural network requires a large amount of resource to be trained. Typically, neural network is trained with multiple GPUs and CPUs. And the device placement problem considers to find an optimal match from each operation of, in the neural network to one of available devices so that the training time of the neural network can be minimized. Recently, Google Brain proposed a method, reinforcement learning method based on policy gradient algorithm to solve the device placement problem. However, due to the policy gradient algorithm, this method is very sample inefficient, and it takes 27 hours and 160 workers to find a good placement to train the neural network. And in our paper, we propose to use a more modern reinforcement learning algorithm, proximal policy optimization, PPO, to solve the device placement problem. And this algorithm, PPO, is developed recently by OpenAI and DeepMind, which achieves much better sample efficiency than policy gradient algorithm. However, in order to apply the PPO to solve the device placement problem, we face a challenge that the device placement problem needs to be modeled as a Markov-optimization process. To tackle this challenge, we designed such a device placement MDP. As this example shows, for placing the first operation of the neural network, we just sample a probability distribution and we get a device recommendation. Here, we get the CPU device. Then we just put that operation on the CPU. For placing the second operation of the neural network, we just sample another distribution and we get a device recommendation such as the GPU 1. Then we just put that operation on the GPU 1. Then this MDP entered to another placement state. Then we continue this process until all operations in the new network are placed. Then we can train this new network with this placement. Then we can get the training time of this placement. Then with this training time information, we just update the set of probability distributions, also called a policy. Then we continue this process until we get a very good placement to train the neural network. We use the capital R to denote the training time of the placement, and we use R bar to denote the average training time of all previous sampled placements. Naturally, we define the reward of a state by R bar minus R. Intuitively, a placement with smaller training time has higher reward. We also use eta pi to denote the expected reward of a policy pi. We use q pi SNAN to denote the expected q value of the rewards under a policy pi. Then we consider the problem, how to update the old policy pi to a new policy pi prime, so that under the new policy pi prime, our expected performance can be improved compared to the older one. Our main results in this paper is to derive a performance lower bound of the expected performance of the new policy. As this equation shows, eta pi prime is greater than the expected q values minus a constant c multiply a KL divergence between the old policy and the new policy. We provide a detailed proof of this lower bound in our paper. And the main rationale of PPO algorithm is that by maximizing the performance lower bound to update the policy, then the expected performance of the new policy eta pi prime can be also maximized. Following this rationale, we just derive such an optimization objective. As the equation shows, we just maximize this performance lower bound to update our policy. Then this is our main algorithm. Initially, the policy pi are just a set of uniform distributions without any preference to choose any device. And then we start to iterate. At every stage n from capital N minus 1, we just sample that distribution to get finally to get a placement. Then we reconfigure the device placement of the deep neural network in the TensorFlow code as the sampled placement. Then we train the deep neural network for 10 steps with this placement. Then we record the training time. Then with this information, we just construct the performance lower bound. Then we maximize the lower bound by performing several stochastic gradient ascent towards that objective. We use a recurrent neural network to represent the policy. The input of this RN is the computation graph of the neural network, and the output of this RN is the set of probability distributions, and we just sample that distributions to get a placement. We conduct our experiment on the Google Cloud with 5 4-GPU machines. We implement our algorithm in the CIFAR-10 image classification benchmark. We also implement a distributed training framework. In this framework, the controller stores the set of parameters of the RNN. Then it samples several placements, and it assigns each placement to one of the workers so that the placement can be evaluated simultaneously on the workers. This often achieves several folds training speed up of the reinforcement learning. Then this is our performance data. As this red solid curve shows, our algorithm achieves much faster performance improvement compared to the Google's policy gradient method for this problem, as shown by the blue solid line. With the placement found by our algorithm, it achieves the training time of the CNN can be greatly achieved compared to the policy gradient algorithm and the single GPU baseline. Also, the placement can achieve the training time of the CNN can outperforms the traditional data parallelism schemes such as synchronous towers and asynchronous towers. Thanks.
All right, well, let's have some questions while the next speaker comes up. Can we have some questions? So I had a question. So why the focus on model-free methods here? Wouldn't it be more sample efficient even if you could actually build a model of these things and do model-based RL?
Oh, okay.
I guess conceptually, why do you want to focus on model-free methods like reinforce and PPO?
Because we use traditionally the Google's paper, they use the policy gradient method. It is a direct policy search method instead of the model-based learning with some value function things. So we just, in order to improve that sample efficiency of that algorithm, so we also adopt a more advanced policy search method, the PPO, to solve this problem. But the use a value-based method might be very promising. It is also one of our future work.
All right, thank you. Let's thank the speaker again. All right, next up we have Lisa Lee, who will be talking about gated path planning networks.
Hey everyone, I'm Lisa, and I'm a PhD student at Carnegie Mellon University. I'll be presenting our paper titled Gated Path Planning Networks. My collaborators are Emilio Perisotto, Devendra Chaplat, and my advisors Eric Shing and Ruslan Salakutunov, who are also from CMU. Path planning is the problem of finding the shortest set of actions to reach a goal location from your starting state. Path planning is a fundamental part of any application that requires navigation. This includes autonomous vehicles, drones, factory robots, and household robots. There are many path planning algorithms, an example being A-star search, which is a popular heuristic algorithm, but it is not differentiable. A recent work introduced a neural architecture for path planning called value iteration networks. Differentiability allows this method to be used as a path planner module within a larger neural architecture, while maintaining end-to-end differentiability. VINs have become an important path planner component used in many recent works, and here are some examples. The wide usage of VINs demonstrates its effectiveness as a path planner. However, despite their effectiveness, VINs are difficult to optimize. To give an outline of this talk, first I will give a quick overview of VIN. Next, we reframe VIN as a recurrent convolutional network. From this perspective, we propose architectural improvements to VIN, which we call the gated path planning networks. Lastly, we show that GPPN performs better and alleviates many optimization issues of VIN. First, a quick overview of VIN. The input is the goal location and the map design, which are both binary matrices and stacked as different channels. The input is passed through a convolutional layer to estimate a reward matrix. This reward is stacked with an initial state value matrix and passed through another convolutional layer to produce estimates of the action state value. The summation here simply denotes a convolution with kernel size 3, and W are the convolutional weights. Let's simplify notation and drop the indices I and J. This notation will denote convolution with kernel size 3. Finally, the Q values are passed through a max pooling layer over the feature channels to estimate the state value matrix V. In the next iteration, we use this new state value to compute equation 1 again. And we repeat this recurrent computation loop for some number of iterations. And finally, we output the last state value, which is a heat map over the maze design. Note that equations 1 and 2 resemble the classic value iteration algorithm. The VIN architecture was designed to mimic the application of value iteration on a 2D grid world. VIN has the advantage of being differentiable, whereas the classic algorithm is not. Next, let's combine these two equations into one line. Okay. This way, we can view the VIN as a recurrent convolutional network, but with an unconventional nonlinearity, which is max pooling, a restriction of kernel sizes to 3, and a hidden dimension of 1. Non-gated RNNs like this are known to be difficult to optimize due to effects like vanishing and exploding gradients. We propose to replace the max pooling activation with a well-established gated recurrent operator, such as the LSTM. We also allow kernel sizes greater than 3, and we call this resulting architecture gated path planning networks. The gated LSTM update is well known to alleviate many of the optimization problems with standard recurrent networks. At the end of the day, it's an extremely simple idea, replacing the max pooling nonlinearity with an LSTM nonlinearity. But the performance improvement is significant, as I will show next. We tested the models on maze environments like this, using a variety of settings such as training dataset size, and maze transition models. In the news transition model, the agent can move one cell north, east, west, south. In more, the agent can move to any of the 8 neighboring cells. In differential drive, the agent can move forward along its current orientation, or turn left or turn right. We also did experiments in the 3D VizDoom environment, where the agent has to learn path planning from first-person RGB images. In the interest of time, I will give a brief overview of the experimental results, but for full details, come check out our poster. We found that GPPN outperforms VIN in a variety of metrics. First is learning speed. Here's the learning curve. On the y-axis, we have percent optimal, which is the percentage of states whose predicted paths have optimal length. And on the x-axis, we have the number of training epochs. GPPN learns faster, and its learning curve also looks more stable. On the other hand, VIN performance oscillates between epochs. Here, we plot the test performance for different maze transition models, news, more, and differential drive. GPPN performs better, especially for the news and more domains. Next is generalization. Here, we vary the training dataset size between 10,000, 25,000, and 100,000. GPPN generalizes better with less data, and as we decrease the dataset size, the performance difference becomes greater. Next is hyperparameter sensitivity. We tested each model using 25 different hyperparameter settings. In this plot, the y-axis is the performance, and the x-axis are the hyperparameter setting indices ordered by performance. The curve for GPPN is flatter, meaning that it is more stable to hyperparameter changes. Lastly, we measure random seed sensitivity. We trained each model multiple times using different random seed initializations and recorded its performance. Here's the box plot showing the amount of variance in performance, and we can see that GPPN exhibits less variance and therefore is less sensitive to random seed initializations. To summarize, GPPN is a more general architecture that relaxes the architectural inductive bias of VIN. It performs better and alleviates many optimization issues of VIN. Our results suggest that path planning architectures need not strictly resemble pathfinding algorithms like value iteration. By looking at VIN as a recurrent convolutional network, we can explore other RNN architectural improvements, including gated recurrent operators, which was the focus of our work, or other RNN improvements that were introduced recently. I'd like to thank my collaborators again, and thanks NVIDIA for providing GPU support. Our code is available on GitHub, so you can replicate our experiments. And come check out our poster later today. Yeah, thank you.
All right, could the next speaker come up while we're taking questions? Hard to tell if people are going to the microphone. Are you going to the microphone? Okay. Here, you can.
When you replace the max pooling nonlinearity with LSTMs, the output loses its interpretation as the value, right? The output of the nonlinearity.
Sorry, do you mean the output of the max pooling?
Yeah.
Yeah, that's the value matrix. That's like estimated by the VIN or the GPP.
Okay, but in the GPNN, if you replace that nonlinearity with the LSTM,
Yeah.
does it lose interpretation as the value?
It still outputs like the same dimension, like the value matrix, but you also have like other like gated cells in the LSTM, so you will have like other like I guess like other like hidden vectors within the LSTM.
Okay, and the second question that I have is that did you compare? Did you have baseline experiments that used just the LSTM without any of the? Did you have any baseline experiments with just LSTMs?
So the original VIN paper compared VIN with like baseline CNN architect and RNN architectures, and they already showed that like VIN outperforms them significantly. So our baseline was the value iteration network.
Okay.
Yeah.
Because I'm okay.
I think we'll take the rest offline. Yeah. All right, then thanks, speaker again. All right, and last up, though I guess the next session starts directly after this one, so it's not really a break. But last up in this session is Chao Tao, who's talking about best ARM identification in linear bandits with linear dimension dependency.
Okay. Good afternoon, everyone. It's my pleasure to talk here. My name is Chao Tao. I'm a PhD student in Indiana University at Bloomington. My topic today is best ARM identification in linear bandits with linear dimension dependency. Unlike others, it is a theoretical paper. The problem is based on linear bandits. Basically, they are in a d-dimensional Euclidean space. There are capital N knowing vectors and a universal unknowing parameter theta. Each pool of ARM xi incurs a stochastic reward, which equals to xi transpose theta plus centered random noise. We also make some assumptions. We assume the rank of input arms is D. Otherwise, we can do orthogonal transformation such that input arms are contained in a smaller space. Second, we assume the 2 norm of the input arms is at most 1, and the 2 norm of the unknown parameter theta is at most capital L. Finally, we assume epsilon is an independent kappa sub-Gaussian random variable. With the knowledge in linear bandits, we can formulate the problem we are studying. Let xi be the arm with the i's largest expected reward, and we assume there is only one best arm. We call an algorithm A is delta correct if it can output the best arm with probability at least 1 minus delta for any instance. The goal is to find such an algorithm while using the smallest number of samples. Linear bandits is very different from the ordinary multi-armed bandits. For example, in this figure, X5 is best arm. At some time, arms X1, X2, X3 may be already eliminated. For the ordinary multi-armed bandits would focus on pulling arms X4 and X5 until some criteria is satisfied. However, in linear bandits, a better strategy would consider pulling arms X1, X2, X3, since they also provide valuable information in estimating the unknown parameter theta. Linear bandits have many applications. For example, clinical trials, advertising and search, and personalized recommendation. Let delta I be the gap between the best arm and the I's largest arm. Saul and Conning proposed 2 algorithms regarding this problem. However, the sample complexities of their algorithm are both dependent on square of dimension d. In our paper, we propose 2 algorithms, Y, elim, tail, and alba, which are both linear dependent on the dimension d. Moreover, our algorithm alba is fully data dependent, which depends on the first smallest gaps, the smallest gaps. The key part of our algorithm is the new estimator vector est, which essentially estimates the unknown parameter theta given a budget of n samples. In the first step, it solves the relaxed G experimental design to derive a distribution over input arms. In the second step, it pulls arms sampled from the IID sampled from the distribution lambda star. In the last 2 steps, it uses the observed rewards to estimate the unknown parameter theta. Note that here a matrix A is not randomized, so we can use existing techniques to derive concentration bounds. For more details of our algorithms, Y, elim, tail, and alba, please refer to our paper. For the experiments, we compare our 2 algorithms with state-of-the-art XY allocation and XY adaptive. All of the algorithms are implemented in Python 3 without parallelization. We set confidence level delta equals to 0.05. For each setup, we run it for 100 independent runs. The average number of samples, average used time, and empirical failure probabilities are compared. Note that for all the algorithms, empirical failure probabilities are 0. We do not list them here. Due to time constraint, we only show the results of the first experiment. For the first experiment, the setup is very similar to the one in Saul's paper. Basically, we set the number of input arms to be d plus 1, which includes d orthogonal basis, and the left arm x d plus 1. The first 2 columns is set to be cosine omega and sine omega. We can see arm E1 and arm XD plus 1 is very close. We set unknown parameter theta to be in this way, such that arm E1 is the best arm. We choose random noise epsilon follows the normal distribution. For all the algorithms, they are tested for dimensions from 2 to 10. This figure shows the average number of samples used for each algorithm. Half of the vertical bar represents the standard deviation. The red ones represent the results of algorithm Y-Lintail, and the blue ones represent the results of algorithm ALBA. This table shows the average runtime for each algorithm. The first column represents the input dimension, and each one of the left columns shows the average runtime for each algorithm. From the results here, we can see our algorithm ALBA shows superior performance in both average number of samples and the average runtime. Thanks. Thanks for coming.
All right, let's have the first speaker from the next session come up and set up while we're taking questions. So any questions? Hard to tell who's just coming and going and who's going for the mic. So I had a question. So presumably there's going to be some dependence on the independence of the different bandits, right? So if two bandits are exactly the same, if you have two optimal ones, of course you can't find the best one. But I didn't understand how you get away from dependence on lower down ones. So if two lower down bandits are not as good, that will make the matrix non-invertible, won't it? And so how do you get rid of that possibility?
Okay. I think in this situation we should do orthogonal transformation to transform them in a smaller space, such that they are of full rank.
Okay. So the A has to be full rank.
Yes.
And there isn't any dependence on sort of slight low rankness. That's okay. We'll take it offline.
Okay. Thank you.
Let's thank the speaker again. All right, next up, this is the Reinforcement Learning 3 session. Next up, we have Mario Sruji, who's going to talk about structured local nets for deep reinforcement learning.
Good afternoon, everybody. My name is Mario Sruji. I'm very excited to be here today. Just a brief introduction. So I'm a rising master's student in CS at Stanford University. And today I'd like to present to you our work titled Structured Control Nets for Deep Reinforcement Learning. This work was done when I was an intern at Apple this past year, along with Jen Zhang, who's in the crowd today, and it was also under Ruslan Salahuddinov, who I'm sure many of you are familiar with. So yeah, let's get started. So in our work, we operate in a reinforcement learning setting. I'll give a brief overview of the setup for those of you who are not familiar with RL. Essentially, RL involves an agent environment interaction, where the agent's goal is to maximize the expected accumulated reward it is to achieve over an episode of a task. So the environment provides an observation to the agent, who then must map this observation to an action through something we call the policy of the agent to essentially receive a reward for that time step. Now, recently there have been many successful demonstrations of RL on numerous environments, and some of those include Game of Go, robotics environments, Atari, and others. So some previous works in this field. Currently, the majority of deep RL work focuses on training algorithms, and thus they use generic multi-layer perceptrons on state or visual embeddings for policy and value networks. So there are several works focusing on the structures of the networks themselves. For value functions, one example is the dueling network, which splits the Q network into a value and advantage head. There are several recent works as well on adding structure and computation for planning, achieving great results on environments that require long-term planning. In our work that I'll show you today, we'll be making improvements on the architecture of the policy network in deep RL, specifically targeting control-specific tasks. So our work is complementary to a lot of the work on value networks and planning networks, and due to this, it can be combined in an orthogonal direction. So our architecture is what we call a structured control net. Essentially how it works is it splits the problem into two streams, a linear and nonlinear control. The output of the network is the addition of these two streams. And the way we train these two streams is we do it together. It's trained end to end. So essentially what we use the nonlinear control here is for higher level complex learning, and the linear control is for local tuning and stabilization. So in our experiments, I'll just explain real quick. The linear control here is essentially comprised of learning a gain matrix K that you multiply by the state to produce your action. I'll go over this in a little more detail in the coming slides. For the nonlinear module in our experiments, we use a standard multi-layer perceptron. However, at the end of the presentation, I will also show a case study where we can actually tailor this architecture to specific types of tasks to further improve the performance. So for PPO or actor, this network outputs the mean of a Gaussian distribution with variable standard deviation. We also use evolutionary strategies as a training algorithm, and in that case, we can actually output the actions directly due to the inherent stochasticity of this algorithm. So I'm going to go over 3 intuitions of why we decided to structure our architecture in this way. So our first intuition comes from motivation by ResNet, which is a very successful network architecture in the field of computer vision. So ResNet is actually able to have great success because of the way its interconnections are structured. Essentially, instead of learning the desired mapping directly, it's easier to learn the residue between the desired mapping and the input itself. And looking at SCN, our structure control net, where the action A is equal to the addition of the linear and nonlinear control modules, we are learning the residue of linear control here. So I will show in a few slides that also linear control on its own is actually quite effective, which is also one of our next motivations. So our second intuition actually is motivated by traditional control theory. So let's take a simple trajectory tracking problem as an example, where we have a desired state we would like to reach, S sub d, provided by planning methods, and a tracking error E, which is calculated by subtracting our desired state from our current state S. So from traditional nonlinear control theory, the control typically has 2 feedback terms, a nonlinear control U sub S and a linear control K times E, which is a gain matrix K times the tracking error. So this is a little bit different than our SCN because of the tracking error and desired state. However, if we substitute the definition of tracking error, the control terms can be converted to a form very similar to our structure control net. So now the nonlinear control term U sub n includes the original nonlinear control term U sub s and desired state k times s sub d. This is important because that means that SCN is also learning the desired trajectory, s sub d, and thus planning implicitly. So now I want to show another motivation by showing the performance of linear control on its own, and that it's actually quite effective. So essentially what I'm showing here is 4 different environments, Majoku environments, trained over 2 million time steps, and I'm showing the training performance in episodic reward over these 2 million time steps. So in blue, we see the linear control model that I described briefly before. It's essentially just doing a matrix multiplication of a gain matrix K times a state to reduce the action, and we are learning that small gain matrix. In orange, you can see a standard multi-layer perceptron with 64 hidden units. Now, as we can see here, and also with other previous works that have been done, linear control is actually quite effective on its own, even though it's quite simple. So this, again, was another motivation for us to go ahead and put this control structure in our architecture. And what I'm going to show you in the next few slides with our results is actually our control net is around 85% smaller than a standard MLP, and we were able to achieve around 17% average improvement in final reward, while also being more robust to noise and working with multiple different training methods. So the environments that we used to test in our experiments, so the first we used is a Majoku environment. So these are essentially physics environments that involve different humanoids and control characters that you can manipulate. We also used RoboSchool, which is another set of environments similar to Majoku that were released by OpenAI. We also used Atari games and also an urban driving environment that we actually created in-house at Apple. Just a simple driving environment to motivate. So we design and test all of our experiments following the guidelines introduced by DRL reproducibility. We also use 3 different training algorithms, actor, PPO, and ES, to show results across all of them. We avoid any environment-specific tuning, we avoid random seed selection, and we also fix the hyperparameters throughout the training. And then in our results that I'm about to show you, we actually average all results across 5 different random seeds for 2 million time steps. And the algorithms, PPO and actor, are the same algorithms that are released on the OpenAI baseline GitHub. So there's a lot of results I'm about to go over, so I'll just go through them briefly. So the first thing I want to show you guys is baseline evaluation. So essentially, I'm going to go through the performance of our structured control net versus a baseline MLP with no specific hyperparameter tuning. And I also want to show you how it generalizes compared to the MLP. After, I want to go into the architecture and actually break down how things are being learned inside the control net. Third, I want to show you what actually happens if we go ahead and tune our model and the MLP for specific environments. And then finally, I'll show you a few applications of this net. So first, once again here I'm showing multiple graphs of Mojoku and RoboSchool environments. These were trained over 2 million time steps, averaged over 5 random seeds, as I mentioned earlier. So in blue, we have our structured control net, which has 16 hidden units. And in orange, I'm showing the multi-layer perceptron baseline MLP with 64 hidden units. So our structured control net here is only 15.6% of the size of the MLP, and we were able to achieve improvement of 13.2% for PPO while using PPO as a training algorithm, and 17.5% using ES. Next, next what we did here was we attempted to see how does our control net generalize compared to the MLP. So what we did was we injected Gaussian noise into both the action and state spaces with varying standard deviation of that noise. So here in the graph, I'm showing we did 4 different setups. We had Gaussian noise injected with a standard deviation of 0.5 all the way up to 2 and steps of 0.5. And we showed what does the resulting performance look like in comparison to the original model, which had no noise injected into it. Now, what we found is that our SCN demonstrates superior robustness against Gaussian noise unseen during training compared to the baseline MLP. So in blue, you can see our structure control net, and in red, you can see the MLP for both state and action noise. So next here, what I'm showing is an ablation study of the modules inside of SCN. So essentially, the structure control net, again, is formed of 2 modules, the linear and nonlinear. So what we did here was we took those 2 modules and also trained them separately. So we took a small multi-layer perceptron of the same size as the one in SCN and a linear model of the same size, trained them separately, and then saw how they compare to SCN when trained together. So in blue here, I'm showing our structure control net performance. In orange, you can see the linear model on its own, and in green, you can see the MLP of the same size, trained separately. So what we found was that our SCN performs better by a significant margin. However, again, as we found earlier, the linear control on its own is actually quite effective. So now, this is looking a little more inside of the structure itself to investigate whether our structure control net has learned effective linear and nonlinear modules. So we conducted 3 tests. So I'm labeling here on the architecture something called SCN-L and SCN-N. So essentially, for the first test, what we did was we compared the performance of a separately trained linear policy that is identical to the one inside of SCN with the post-trained linear policy inside of SCN. So essentially, we took our post-trained SCN, froze the nonlinear output, only used the linear output, and compared it to a linear model that is trained separately on its own. And what we found was that the linear model inside of SCN, after freezing the nonlinear output, was actually able to achieve about 65 to 68% of the performance of the separately trained linear model, which was motivating because that means the linear stream is actually learned effectively. The second test we conducted was very similar to the first. We froze the linear module's output inside of SCN and only looked at the MLP's output, the nonlinear control output, and we compared it to a separately trained MLP. Now, the nonlinear control module inside of SCN was only able to achieve about 8 to 9% of the performance of the separately trained MLP, which shows that you really need the linear stream to stabilize the nonlinear output in this architecture. Now, finally, the third test. What we did was we naively assembled a post-trained structure control net. So what that means is we took a separately trained linear model, separately trained nonlinear MLP, and then combined them to form structure control net and compared it to an SCN that's trained together. And what we found was that the naively assembled SCN was only able to achieve about 18 to 21% of the performance of the actual SCN when trained together, which was also very motivating because we want this control net to be trained together with both streams at the same time. So here what I'm showing is the performance of SCN when we actually tune each hyperparameter and also choose and also vary the model size for each environment. So essentially what I'm showing here is we tested across 12 environments, and what we did was swept the nonlinear module sizes across a set of 64, 32, 16, 8, and 4 hidden units. And what we found was even when we tuned SCN and tuned the MLP for each environment, we were still able to achieve about 10.7% improvement on final reward and about 14.2% improvement on average reward. So I'm going to speed through a little more because it looks like I'm low on time. But essentially, here what I'm showing is this is our urban driving environment that we made in-house at Apple. And essentially, we wanted to see where can we apply this structure control net? What type of applications? So on the top, I'm showing a right-hand merge where the blue agent in blue, which is the lured agent, has to learn to merge with oncoming traffic in red. On the bottom, I'm showing an unprotected left turn where the blue agent must learn to yield to oncoming traffic. Essentially, the goal of the blue agent is to do this as quickly as possible while also being extremely safe. Any crash results in a very large negative reward, and reaching the goal results in a very large positive reward. So once again, we used ES and PPO as the two training algorithms, and we compared the MLP performance with our SCN, and we found that SCN was superior in performance. Next, we show results on Atari. So we tested across 60 different Atari games, and what we did is we tested for 10 million, we ran training for 10 million time steps, which equals to approximately 40 million frames. Each learning curve and metric is averaged across 3 to 10 million time step trials with different random seeds. So SCN here uses the same convolutional layers and critic model as in deep Q networks, but the learned visual features are flattened and then fed into the linear and nonlinear modules of SCN. So what we found here is our SCN network was able to actually win about 35 games compared to 25 for the MLP 512. So the MLP here has 512 hidden units versus our SCN, which has 8 hidden units. So finally, I want to go quite quickly through this case study, but it's quite interesting. So as I mentioned before, we used the MLP in our nonlinear module, but you don't actually have to do that. So what we did was we took a case study on locomotion. So essentially, locomotive environments require rhythmic patterns. And what we did was we wanted to emulate something called central pattern generators in our nonlinear module instead of using an MLP. So essentially, CPGs are biological neural networks that can produce rhythmic patterns without need of higher control centers, and they underlie a lot of behaviors in animals today. So essentially, how we did this emulation is we combined the output of 16 different sinusoids, where we learned the amplitude, frequency, and phase. And this allowed us to produce a rhythmic type of activity in our nonlinear module. So this, what I'm showing here, is an instantiation of structure control net. We call it locomotor net. So essentially, again, the linear module is untouched from before, but we replaced our nonlinear MLP with this CPG emulator. And the interesting result that we found was, here I'm showing blue is our locomotor net, which is the instantiation of SCN that uses the central pattern generator emulation I just showed. In orange, I'm showing the original structure control net that uses the MLP in the nonlinear module. And then in green, I'm showing the standard MLP 64. So by tailoring SCN to this specific case study, we're actually able to further improve performance and sample efficiency. So this is really showing how you can actually tailor this control architecture to different types of tasks by providing these priors. So finally, for future work, we'd like to continue to validate our structure control net on new environments. We'd also like to explore the incorporation of a planning module into an SCN as a possible third stream for more long-term behavior. We also want to explore more ways to tailor SCN to different types of tasks and environments, and we actually encourage exploration in this area. So if any of you are interested to talk more about this, please come see our poster today. It's in Hall B, poster number 42. Yeah, I'd love to answer any questions, and thank you.
All right, if the next speaker can come up while we're taking questions. Yes.
So that's pretty cool, thank you. And did you think, so linear control would be optimal for a quadratic system, right? We know that. So did you think of both, maybe empirically, you can also do that theoretically, quantify the type of quadraticness of your problem and see how good this model is, like how correlated the environments with the, the strength of the method?
Yeah, so this is actually...
also do that theoretically, by the way, right?
Yeah, so this is actually a very good question. So we're actually still exploring more theoretical background and more theoretical justification for this architecture. So it's also going to be part of our future work, but yeah, good point.
Oh, thanks.
All right, let's thank the speaker again. All right, next up we have Thomas Harnoja, who's going to talk about latent space policies for hierarchical reinforcement learning.
Okay, thank you. So my name is Tuomas. I'm going to talk about latent space policies and how we can use those to form hierarchies for reinforcement learning. So this is a picture of my office, and here is my workstation. If I want to navigate to my workstation, I can easily come up with a plan in my head because I don't need to think about the low-level actions that I send to my muscles, but I can think about it in terms of higher-level abstractions, for example, directions in which I want to move. So this is the idea behind hierarchical reinforcement learning, where we split the policy into multiple stages, and each stage is responsible for providing these skills at different abstraction levels. For example, the low-level policy can provide us primitive skills, for example, skills of moving into different directions, and the low-level policy only needs to focus on the details of the task, whereas the high-level policy then can choose among these primitives and to solve more complex tasks. And the high-level policy only needs to focus on the abstract features, and therefore it generalizes across different situations. There are other benefits of using hierarchies as well. For example, better exploration. If we explore in the torque space, we don't get very far. But if we explore in the space of directions, then we can get a much better coverage of the entire state space. The other benefit is reusability, because the low-level policy only focuses on the details, and the details are the same among different tasks. We can reuse the low-level policies in these tasks and only train the high-level policy. There are many ways to train these hierarchical policies, and depending on how we train them, we have different challenges. One way is to train them in top-down fashion, which means that we train the entire hierarchy end-to-end. When we do that, we need to make sure that we are not converging to degenerate solutions, which means that only one of the primitives is responsible for producing the entire solution to the task, and the high-level policy can then just learn trivial solution where it always chooses the same primitive. The other way of training these policies is bottom-up training, where we first train the low-level policy to provide us useful primitive skills, and then we train the high-level policy. When we do that, we need to make sure that the low-level policy learns useful skills, and we get the full coverage of the primitives that are required for solving the high-level task. Because of these challenges, when we train these policies end-to-end, we need to focus on the architectural design. For example, feudal networks, they have a separate worker network and a master manager network, and the manager is responsible for guiding the learning of the worker in order to avoid degenerate solutions. On the other hand, if we use bottom-up training, we need to focus on the primitive skills and to make sure that we get the full coverage of all the primitives that we need. For example, Florenza et al., they maximize the mutual information between the primitives and the parts of the state space that matters for solving the task. For example, in the locomotion skill, we are interested in primitives that have a good coverage on the XY coordinates. So we maximize the mutual information between those coordinates and the primitives. This, of course, requires some domain knowledge. Our method is also can be considered as a bottom-up training method, but there is one key difference. We require that the higher levels can always override the decisions made by the lower levels. We do that by using special kind of policies that are invertible, and therefore the high level can always invert the actions taken by the low level policies. Because of this, we can think about learning our policies as if they were the only policies in our system and not part of the bigger hierarchy. The second point is that we don't require any domain knowledge, even although we can use shaping rewards to accelerate training. To give an overview of our method, it's based on maximizing the entropy. And on this video, okay, it's not playing, but anyway, the video is showing multiple rollouts from a single policy. And these maximum entropy policies, they have high entropy, so that's why they give diverse behaviors, which is exactly what we need for our, which is very useful for learning hierarchical policies. Our policies are based on normalizing flows, and normalizing flows represent the policy as an invertible mapping, and that's why we get this property of non-crippling. That's why the low-level policies are non-crippling, and they don't cripple the behavior of the high-level policy. Our policies have a latent space, which makes them stackable. We can always think about the latent space of a low-level policy as the action space for the higher-level policy. I will next talk about the derivation of our method and a little bit about the implementation. I will start with describing maximum entropy reinforcement learning, and then I extend that discussion to learning hierarchical policies. Finally, I will talk about normalizing flows, which is a way to represent very expressive policies. Maximum entropy reinforcement learning is based on the duality of control and inference, which dates back to the 1960s, and it was later extended to cover also a more general case in 2008 by Todorov. In control problem, we want to answer the question, what is the action to take right now in order to the future to be optimal? On the other hand, in the inference framework, we ask a related question, namely, what is the action which was taken, given that we already observed the future was optimal? It turns out that at the limit, the answer to these two questions is exactly the same. And when we are dealing with the inference framework, it's useful to think about graphical models. So here is a Markov decision process where we have a sequence of states which are conditioned on the previous state and action. In order to connect these to optimal control, we define new random variables, optimality random variables, which are binary valued. So they take the value true whenever the corresponding state action pair is considered optimal. To connect this to reward function, we specify the probability of being optimal as to be equal to exponentiated reward for that state action pair. And finally, we condition on all these optimality random variables, and we pretend that we observed all of them to be true. Now the question is, what were the actions that were actually taken? And those actions conditioned on the current state and optimal future, that's our optimal policy. We can show that the optimal policy, in this case, it optimizes the maximum entropy objective, where we are not only optimizing the reward, but also the entropy over the actions. There are several algorithms that can find these optimal policies. For example, soft key learning, soft actor critic, and path consistency learning. They all work in continuous domain, and the first two of which can be considered as performing message passing in the corresponding graphical model. There are also other algorithms that work in discrete domains, but in this work we are considering continuous actions, so in principle we can use any of the first three methods. Then how to extend this to learning hierarchical policies? This is again the same graphical model as before, and suppose that we run our inference algorithm and we find an optimal policy for some task, and we represent the policy using latent space models. That means that our actions are conditioned not only on the state, but also some latent vector h, and which follows some prior distribution p of h that we get to choose. Now that the actions are fully determined by the latent and the state, we don't actually need to worry about or think about the actions anymore, and we can simply abstract them away. We can do that by integrating out the actions, which essentially means that we are combining the dynamics model and the optimal policy. That way we are shaping the dynamics in a way that the new dynamics have the optimal behavior more likely. We don't actually need to do this integration, but this is just to demonstrate what is going on there. Now, if you look at the graphical model on the right, semantically has exactly the same. It looks semantically exactly the same as the first one, which means that we can repeat this procedure multiple times. Here is another illustration. This is an environment that takes in the action. And suppose that we train a stochastic neural network to represent the latent space policy, and the network takes in the latent and produces the actions. And once that neural network has been trained, we don't need to worry about anymore about the actions, so we can abstract away the actions and think about the neural network as being part of our environment. Now we can repeat the process, train another neural network that takes in some other latent vector h2 and produces the latent vector h1. And we can do the same thing, abstract away h1 and think about the second network as being part of the environment. And we can repeat this process multiple times. The key here is to note that each of these layers have exactly the same structure. So this is completely homogeneous structure, which allows us to repeat the process multiple times, and this generalizes to arbitrary number of layers. So how to represent these latent space policies? We use normalizing flows. Normalizing flows makes use of the change of variables formula. So suppose that we have a random variable x that follows some prior distribution p of x, and then we define a new random variable z through an invertible transformation f. Then the density of z can be written in terms of the density of the prior density and the Jacobian of the transformation. We can use this for learning for policies if we write out the action in terms of the latent through an invertible mapping f, and also condition the mapping on the current state. As long as this mapping is invertible for any given state, we can write out the density of the actions in terms of the prior and the Jacobian of the transformation. In practice, we implement these normalizing flows in the following way. This is showing a hierarchy of 2 levels. Each of these levels have internally exactly the same structure. So let's look at inside one of them. Inside these layers, we have 2 components. First, we have an embedding network, which processes the states and produces a state embedding. This network can be represented with an arbitrary neural network, as this doesn't need to be invertible. But then we have 2 invertible layers, which are called coupling layers. They are similar to what was proposed by Din et al. In density estimation using a real NVP paper. Only difference is that we are also conditioning on the state embedding here. The nice thing here is that because these green layers are invertible, we can always, when we learn the second layer can learn the inverse map and thus override whatever the lower level is doing. For training, we use soft actor predict, which is a recent method for a maximum entropy reinforcement learning. Finally, I'm going to talk about the experiments. So first, to test if our latent space policies can be used to train standard benchmark tasks as they are without using hierarchies, we trained on several Muchoco tasks, and we are comparing to SAC with Gaussian mixture models. So our latent space policies are shown in blue, and the Gaussian mixture models using otherwise exactly the same implementation are shown in orange. And as you see, our method, it can perform comparably in all of the environments, and in the hardest environments, we get a small performance boost. But the main point of our latent space policies is that we can stack them. So what happens if we stack multiple policies on these standard benchmark tasks? This is a humanoid with 21-dimensional actions, and this learning curve is still showing the same learning curve for a single level policy from the previous slide. And what we did next, we froze the low-level policy after 10 million time steps. And at that point, we stacked another policy on top of it and kept training. And when we do that, we get a significant performance boost. We think that's because at the point of freezing the low-level policy, it stops forgetting, and at the same time, it is shaping the dynamics by making it much easier to learn for the next level. And I want to emphasize that both of these levels were trained with the standard reward function, so no extra information was used here. Next, we demonstrate how we can use these hierarchical policies to train for tasks that require some shaping reward. So we trained the low-level policy to maximize the agent to maximize the speed and also the entropy. And oh, now it's playing. It's not playing on my screen. So this video is showing multiple rollouts from a single policy, and we use this as our base policy for solving a sparse reward task. So then we froze the low-level policy, and we trained another policy on top of it. And this time the task is to navigate through the maze to the green area, and when the agent gets there, the episode terminates and the agent gets a reward. And we can repeat this on multiple different high-level tasks to navigate into different regions in this maze. And all of these cases, we are reusing the same base policy. So how does this compare to baselines? In this figure, I'm comparing the final distance, so lower is better in this case. If we simply train a single level policy on the task reward, because the reward is sparse, we never observe the reward and we make no progress. We can think about shaping the reward itself by adding the two rewards together. So this time we are adding also the reward for the speed, and we start seeing some progress. But the problem is that now we have a residual error, and that's because we are no longer optimizing for the same objective, but for a different objective that has this shaping reward included. On the other hand, if we use the hierarchical learning approach and we only train the higher level policy, we start seeing progress immediately and we don't have problems with the residual error. But I'm not including the time steps here needed for training the low-level policy. And that's because we can always amortize the cost of training the low-level policy across multiple tasks. It took 4 million steps to train the low-level policy, so even if I included that in this picture, our method would be still better than the baselines. So to conclude, maximum entropy reinforcement learning with latent space policies, it provides diverse behaviors, it leads to natural formation of hierarchies, and policies based on normalizing flows can be stacked to construct homogeneous hierarchies, and they are invertible and thus non-crippling. So we have released our code, and with this I would like to thank my collaborators and thank you for listening.
All right, the next speaker can come up while we're taking questions.
Hello, can you hear me? Yeah. My question is about the diversity element. So sometimes, like if an agent needs to go north, it might be going to the east a little bit and west a little bit while mostly going north. And that sort of diversity might not be interesting. So do you have any sort of comments on how the maximizing entropy leads to the kind of diversity that might be of interest?
Well, our latent space is continuous. So even if there is, we can always have a latent that corresponds to moving north always, or any other direction. So that would be what we described. That would be a problem if we have a discrete set of primitives. But in our case, the high-level policy can always find a latent that corresponds to moving into exactly the direction that we want.
Yeah. Okay. Thanks.
So I had a question. What was I didn't see sort of a slide showing the value of the invertible policies. What happens if you don't use an invertible policy, especially in the stacked case?
Okay, so we don't have the experiment, but and one reason is that we need these low-level policies, they need to be really expressive. So in order to have an expressive policy, there aren't that many ways to represent those, and normalizing flows provides a good way for that. So we are missing the experiment where we actually show that low-level policies can be inverted. That's a good question.
All right, let's thank the speaker again. All right, next up we have Andrew Liu, who'll be talking about self-consistent trajectory autoencoder, hierarchical reinforcement learning with trajectory embeddings.
All right, hi everyone. My name is Andrew Liu, and I'll be presenting the self-consistent trajectory autoencoder, hierarchical reinforcement learning with trajectory embeddings. Okay, let's jump into it. So imagine you want to go grocery shopping. What are some of the things that you would have to do? Well, to start, you have to get to the store, you have to pick out your items, and then go to the checkout, and so on. We can break down each of these tasks into further subtasks. For instance, if I want to go to the store, I have to plan out a route and maybe get into my car and drive to the store. And this is kind of the main idea behind hierarchical reinforcement learning. How can we enable agents that can take advantage of this hierarchical structure in the task? One form of hierarchy that we consider is reasoning in terms of these low-level skills. Why might this be useful? Well, if I know how to walk, I should be able to reason in terms of where I want to walk to, instead of reasoning at the level of torques and joint angles. Moreover, if I want to plan over long time horizons, you can imagine it's very hard for me to plan out every second of my day versus planning in terms of these low-level skills. So there's a number of challenges in hierarchical reinforcement learning. The first question is, how do you represent these skills? There's been prior work on looking at discrete options, but discrete options are finite, and they might not have all the set of skills that you need to solve a certain task. So maybe what you want here is a more continuous representation of skills. And if you can represent skills, how do you actually learn them? So there's been prior work on specifying hand-specifying objectives for learning these skills, but ideally you want something that's more generic and can work for any task. Planning over long time horizons is also very challenging. If I were to use a model predictive control method, very quickly the model will accumulate errors, and your imagined trajectories might be very different from the reality. So ideally what you might want here is being able to model closely behavior over long trajectories. And finally, a lot of hierarchical tasks have delayed and sparse rewards. And to deal with these, there's been prior work on looking at exploration methods. And one method that we'll consider today is looking at maximum entropy-based exploration. And so in designing our method, we took all of these challenges into account. And so our method, we do learn a continuous representation of these low-level skills. And we use maximum entropy-based exploration to learn a diverse set of skills. And we plan in the space of these learned skills using model predictive control. And so we alternate between these three steps in our method. And the first question you might have is, how do you represent these skills? To do that, I'm going to introduce the self-consistent trajectory autoencoder, also known as sector. So sector draws upon the variational autoencoder, and just like the variational autoencoder, you have an encoder network which takes in a trajectory or a sequence of states and produces a distribution in the latent space. We also have a decoder, which we call the state decoder. This takes a given latent code and produces a distribution over trajectories. And the most important part in sector is the policy decoder. So the policy decoder takes actions in the environment and induces a distribution over trajectories that are realized in the environment. And we train the policy decoder to be consistent with the state decoder, so that given any latent code Z, the distribution of trajectories imagined by the state decoder should match those realized by the policy decoder. So we train this policy decoder using reinforcement learning and the state decoder using supervised learning. And because of this consistency objective, given a latent code Z, the policy decoder, or the state decoder, can be used to imagine how the policy decoder would behave. So the state decoder then can be used as a natural model of the behavior for the policy decoder. So I have this representation. Now, how do I learn a diverse set of skills? Where does the data come from to train the sector model? To do this, we have a maximum entropy-based exploration method where we maximize the entropy of the distribution of trajectories. We optimize this objective using model-free RL. And what this might look like is you sample a number of trajectories under the current policy, and now I want to reward each of these policies using the negative log density of the trajectory. And where might I estimate, how do I estimate that density? To do that, we actually use the sector model as a density estimator. So I pass each of these trajectories through the sector model to get a density estimate, and this encourages the policy to learn a diverse set of behaviors that are unlikely under the current sector model. So now I have these low-level skills. How do I actually solve hierarchical tasks? To do this, we use model predictive control in the latent space. So the sector model learns a lane distribution over skills. Let's say I sample one lane code in that space, and now I'm going to pass it into the state decoder. The state decoder is going to imagine some trajectory in my world, and I can repeat this. I can sample another lane code, imagine a second trajectory, and so on. And I can do this multiple times for many trajectories. And now I'm going to use the reward function to evaluate the reward on each of these trajectories, and I'm going to pick the best one. Let's say the top one happens to have the highest reward. Now I'm going to go back, look at the lane code that was used to generate that first trajectory. I'm going to pass it into the policy decoder, and since the policy decoder is trained to be consistent with the state decoder, that policy decoder is going to execute the trajectory in the environment. And I'm going to repeat this process of using the state decoder to imagine trajectories, ranking using the reward function, and executing using the policy decoder. And to recap, sector has a lot of advantages, including this continuous representation of skills, using entropy-based exploration to collect data that's diverse, and also planning in the space of these skills using model predictive control. And since we are using a model-based method, we have the nice sample complexities of model-based methods. So now I'm going to go over some of the experiments that we did. So the first one is this wheel navigation experiment where we have a cart, and it's given a reward of 1 after reaching every third goal in the sequence. So this is a very sparse reward. We compared this method against a number of prior works. So our method is in the red here. And the green one is VIME, which is an exploration method. We see that VIME is able to perform the task effectively after an order of magnitude more samples. Meanwhile, TRPO, which is a model-free RL algorithm, struggles to receive any reward signal in this task. And MPC struggles with planning over these long task horizons. We also looked at an object manipulation environment where the agent can pick up and move blocks around in the environment, and its goal is to move each block to the correct goal in the correct order, and it's given a reward of 1 after each block reaches the correct goal. And so we compared this against all of the prior baselines, in addition to some new baselines, including A3C, Option Critic, and Feudal. We found that only the sector method was able to produce some meaningful behavior in this task. And we think that this might be because of the very sparse reward in this task, the discontinuous motions dynamics, including picking up the blocks, as well as the very long time horizon. So I want to thank all my collaborators, and do check us out at our poster tonight. There'll be more details and experiments. Thank you, everyone.
All right, we have time for some questions.
Yeah, I was just wondering, how do you, so for MPC you have to have the model and all the rest didn't use the model?
So in our method, we train the state and policy decoders to be consistent. So the state decoder acts as a model.
Okay, so basically you can leverage the model and the other methods cannot, I guess.
So we did compare against a model predictive control method that did try to model the environment, but it modeled the environment at the state level.
Okay, thanks.
Did you feel like using sector for itself for density estimation was sort of a bug or a feature?
we found out it was kind of convenient because we did have the density estimate. Yeah.
Are there things that you found it couldn't do, like that you think another method might be able to help with?
Not sure, but maybe we can discuss that offline.
All right, I think we have time for one more question, maybe while the next speaker comes and sets up. Maybe let's just thank the speaker. All right, and our final talk of the session is from Matthew Smith, and we'll be talking about, I can't quite see the first name of the thing there, so let me schedule up, an inference-based policy gradient method for learning options. Sorry, I just can't see, where's the screen show? It's usually slideshow? Yeah. Cool, sorry about that.
Cool, hey everybody. I'm Matt Smith, and I'm talking about work that I did in collaboration with Herke Van Hoof and Joël Pinot at McGill on learning abstract behaviors in reinforcement learning. And so, a good first question to ask yourself when you're working with this kind of thing is why bother learning abstraction? And I feel like over the last couple of talks, we've sort of gotten a good sense of that. But just to sort of put my spin on things, abstraction is important for scaling learning. We want to learn in more complex or long-term environments, and so we need to sort of abstract and generalize over the specific details of either our states or our perceptions, which is something we're really good at through deep learning. Or we can also do that for actions and behaviors. And so sort of the running example that I like to use for that is that if we're sort of driving to grandma's house, we don't want to think about that in terms of steering angles and pressing the gas. We want to think about, do I want to take the highway or do I want to take the back roads? So just to make sure we're all using the same language here, often this kind of temporal abstraction or abstract behavior is represented through the options framework. And the idea is that rather than take decisions at sort of every single step in our MDP, we have this hierarchical structure wherein we have a sort of policy over options, which selects sub-policies or option policies to use for a little while. Those policies terminate, and that higher level policy is sort of queried again. And we trust that that sort of upper level policy learns to coordinate these lower level policies in order to get done what we're interested in getting done. This work was very much done in the context of the option critic architecture, which is work that's been referenced heavily today by Pierre-Luc Becon, who is also from McGill. And the idea behind option critic was that there was this policy gradient method that we can do that allows us to learn options in this end-to-end manner. And it does that by leveraging this sort of state augmentation trick where we add our options to our state representation sort of under the hood. The problem with that, or the challenge that's associated with that, is that it means that we can only sort of, our Markovian assumption has to stay satisfied, and so we can only really learn those option policies from experience within those options. Which sort of imposes a lot of extra cost on having this hierarchical structure because we could have two different behaviors in the same state that don't share any information, and so ideally we would like that. And so that's the main contribution of this work, was that the idea was that instead of explicitly remembering which options we were acting according to in any given state, we maintain a distribution over which options we could have been acting according to. And that lets us, it sort of leads to two main benefits. We get improved sample efficiency because we're reasoning over all of our options at once, and so we don't have to only learn from whichever one we were actually behaving according to. We can learn from all of our experience in the environment for all of our options. And incidentally, we found that when we applied this method, we had improvements in option specialization and interpretability, which I'll talk more about when we get to results. One other thing I want to note here is that this sort of represents off-policy learning at almost the exact sort of right level. We care a lot about sort of what states and actions we're actually living. You know, that's the difference between sort of crashing a car and not. But we would still like to reason off policy at the abstract level, because when we're sort of, whether we take the garden path or the highway, those both represent driving experience, and ideally we'd like to share that information, that experience to learn from. So for those of you who speak a little bit more math, the idea here is that we're optimizing almost the exact same thing as your classic sort of reinforced policy gradient objective. But you'll notice that because of these latent option variables, information can be passed between actions. And so you can see that probability term has some extra conditions on it versus sort of your normal policy gradient. Then the idea is that sort of we marginalize over those latent variables, which is represented by that M term, which sort of carries that extra information, and it represents exactly what option we're in, or what's the likelihood we're in any given option at that point in the trajectory. And that seems like it would be a really hairy quantity to compute, but it turns out that our behavior model is almost exactly, sort of under these latent option variables, is almost exactly a hidden Markov model. And so we can just use the forwards algorithm to compute that, and it has sort of also recursive gradients, and so we can sort of compute that efficiently, recursively, in terms of our parameterized policies. So we did a set of experiments on sort of the classic Mujoko continuous testbed. Oh, one other thing I wanted to mention here is that because we're just sort of optimizing the classic policy gradient objective, we can use all of our tricks that we've developed over the last several years, like A3C and auxiliary tasks and GA and all these things. So we did a set of experiments in the sort of standard gym Mujoko environments, and here are some results. I'd like to mention that none of these we compared an A3C sort of style implementation of our policy gradient, an A3C style implementation of option critic, and sort of classic A3C, and none of these methods are really state of the art anymore in sort of terms of raw performance. But we found that our method, sort of, despite the fact that it learned a much more complicated policy than that learned by A3C, it was able to, sorry, I'm just keeping time. It was able to learn as efficiently as A3C was, just a single flat policy, whereas Option Critic, which isn't able to share this information between options, sort of suffered under the burden of these extra parameters that it had to learn. So then the question is, if we don't learn faster, then why would we want to learn this sort of hierarchical structure at all today? And while that sort of question, I think, is still being realized by the community in general, one feature of our method in particular is that we found it made our behavior more interpretable. And so here you can see these two bars represent option activity at different points during two trajectories, one during training and one after training. And you see that this yellow policy is active sort of halfway through training, but then after training, it's never used. And we found that very interesting because when we looked at the policies, we found that the red and blue policies, the red and blue options, represented sort of high reward policies, but they needed to be coordinated quite precisely in order for the agent to stay alive. And so while the policy over options was still learning, it sort of included this third policy that was sort of all learned autonomously, which represented a lower reward but more stabilizing policy that allowed it to sort of learn to coordinate these other two behaviors without dying. And so here's some other results that I'm not going to get into because I want time for like maybe one question or two. And so I hope to see you at my poster for more details. Thank you.
All right, so time for some questions.
Thank you for the talk. Have you considered looking into transferability? Like now that you have learned these options, maybe you cannot do as well in the same task, but maybe if you do something similar, they can help you.
Yeah, that's certainly a good question, and we certainly looked into it sort of initially. Those results haven't made it into this paper. It's certainly a question, like a good answer as to sort of why would we want to learn options, because we have this sort of nice structure, and now the idea is that this sort of policy over options can coordinate these things. We found that sort of for our particular optimization and sort of the methods that we used weren't super stable all the time, and so it ended up being sort of a bit of environment search to find the right sort of transfer experiments to do, such that we could learn that way, and we didn't think it was right to include those experiments in the paper. But that's certainly a question sort of that's being looked into.
Thank you.
Thank you.
All right, well, we're right on time, so let's thank all the speakers again in the session.